Morning everyone. Welcome to Tejasri Electrical Engineering YouTube channel. In this video, we have to learn online course Electrical and Electronic Measurements, Part A Electrical Measurements, Chapter 2 Basics of and Instruments. Topics: Electromechanical indicating instruments, deflecting, controlling, and damping forces of an electromechanical indicating instruments. Basically, there are three forces are required for any and instruments for satisfactory operation. Those are: deflecting force is required for the pointer moves from its zero value or initial position. Controlling force, it is required for the pointer to indicate a definite value of measured quantity. Damping force, which is required for suppressing the oscillations of the pointer at steady final position. We have to learn this one by one. Generally, there are three torques are required for any indicating instrument for satisfactory operation. Those are: deflecting torque, which is primarily responsible for deflecting the pointer from its zero or initial position. Next, another one, controlling torque. It is required for equal and opposite force produced against the deflecting torque. Then the pointer indicates the measured value at a steady final position. Deflecting torque equal to controlling torque. Then the pointer indicates the measured value. If the controlling torque is absent, the pointer will reaches behind its measured value and reaches the full scale value. There is no force against the deflecting force, that's why it is reaches the full scale value. If the controlling torque is absent, the pointer will not comes to zero position even after deflection force or deflecting torque or measured value is removed. Next, another one, damping torque. At the final steady position, deflection torque equal to controlling torque. The pointer takes the time to settle at the measured value and it oscillates around the measured quantity, measured value. Therefore, to suppress these oscillations, damping torque is required. Number 1, deflecting force. The deflecting or operating force is required for moving the pointer from its zero or initial position. This force can be produced by utilizing the effects which are discussed in previous video. These effects are magnetic effect, heating effect, electromagnetic or induction effect, electrostatic effect, Hall effect. By using these effects, we have to deflecting the pointer from its zero position. This deflecting force of an instrument converts the electric current or potential into mechanical force, which means moves the pointer from its zero position. The deflecting force is the primary responsible for deflecting the pointer. Number 2, controlling force. The controlling force is required to an instrument to make the pointer deflection in proportional to its magnitude and indicate a definite value. The function of a controlling force are to produce a force equal and opposite to the deflection force of the pointer at the final steady position. In order to make the deflection of the pointer a definite value for a particular magnitude of the measured current, if the controlling force is absent, the pointer will reach behind the final steady position for any magnitude of the measured quantity, and pointer indicates the indefinite value, which indicates the final full scale value. And the controlling torque is required to pointer to bring back to its initial or zero position when deflection force is removed. The measured quantity is removed, then it is bring back to zero position. We have to need controlling torque. If controlling force or controlling torque is absent, the pointer will not come to zero when measured quantity or deflection force is removed. There are two methods to produce controlling torque. There are spring control and gravity control. Number 1, spring control. In this method, two air springs P and Q are mounted in opposite direction on the spindle as shown here. This spindle is pivoted between two jowl bearings like this. A pointer is mounted on the spindle which reads the measured quantity on the scale. When a measured quantity or a deflection force is applied to the instrument, the spindle is rotates, which deflects the pointer on the scale. The two springs on the spindle, which opposes the rotation of the spindle, which produces the opposite force or opposite torque to the deflection torque. Then the pointer indicates the definite value on the scale. If the springs are absent, then the pointer indicates the full scale value, which not stoppable at the definite value. If the springs are not available, this pointer will not come to zero position when deflection or measured quantity is removed. The main required properties of springs: they should be non-magnetic, they should be free from mechanical fatigue, the springs carries the current, then it should have low resistance value. The springs have low resistance temperature coefficients. Generally, the springs are made up of phosphorus bronze. In some of the instruments like moving coil, milliammeters, beryllium copper is also used, but it is very costly material. Here, one form of the control springs mounted is shown above. The inner end of the spring is attached to the spindle and the outer end carries a spigot which engages in a circular disc surrounding the jowl screw. The thickness of the spring is T and this width is B. For a flat spring spiral, controlling torque developed by the deflection is controlling torque Tc equal to EBTQ by 12L into deflection angle theta Newton meters. Here E equal to Young's modulus of spring material. It is measured in Newton per meter square. Here B equal to width of the spring and T is the thickness of the spring, and here L is length of the spring. Theta is angular deflection of the spring. Here E, B and L are constant for a particular spring. Then the controlling torque Tc equal to K into theta. Here theta equal to deflection angle. The controlling torque is directly proportional to deflection of the pointer. Here K is spring constant or control constant or torsion constant or restoring constant, is equal to EB TQ by 12L. It is measured in Newton meters per radians. The disadvantages of spring control. By using the spring control, the scale is uniform because the controlling torque Tc is directly proportional to deflection angle, angular moment theta. Then scale is uniform. The weight of the 8 springs is very low. Then it have low weight. This instrument is placed in any position. It is placed in horizontal or vertical position. Some disadvantages also there. Number 1, since springs are very delicate, the accidental stress may damage them. Small stress is occurred on the springs, it will damage the whole controlling system. If the change of the temperature, the length of the spring also varies, which means controlling torque is also varies. The deflection of the pointer is also varies. Due to fatigue, springs deteriorates with the time. As the age of the springs is increases, then its effectiveness of the spring control torque is also decreases. Controlling torque produced by the gravity control method. In this, the controlling weight W is attached to the spindle as here, and a weight balancing and zero adjusting is mounted on the spindle, which also provided the pointer to indicate the value on the scale as shown here. The principle of gravity control method is based on natural downward pull due to gravity. In this gravity control, a small weight is placed on the arm attached to the moving system. When the moving system is in deflection position, this weight is produces controlling torque. The position of this weight is adjustable for varying controlling torque. A gravity control is often employed in moving iron instruments. In gravity control system, controlling torque is WL sin theta. The controlling torque is directly proportional to sin theta. At final steady position, the deflecting torque equal to controlling torque, then indicates the different value of the measured quantity. This controlling torque is directly proportional to sin theta. That means scale is not uniform. The advantages of this gravity control method is it is simple method to provide control torque. The control torque varying very easily by adjusting the controlling weight. And this gravity control is not affected by the temperature. It is free from fatigue. It doesn't deteriorate with time. It is very cheap. The disadvantage of gravity control. The weight of moving system is increases due to control weights used in vertical position only. That's why it is not used in instruments. The scale is also not uniform because controlling torque Tc is directly proportional to sin theta. It is not suitable for the portable instruments. With gravity control, the scale is cramped at the lower end and expanded at the upper end because the controlling torque Tc is directly proportional to sin theta. The function of the deflection angle is in sinusoidal. That's why the scale is cramped at the lower end and expanded at the upper end. Next, damping force. Damping force is required for the pointer quickly comes to its final steady position without overshooting. At deflection torque equal to controlling torque, the pointer oscillates around the measured value on the scale. To suppress these oscillations, damping force is required. Deflection of the pointer versus time diagram is seen here. There are three types of damping systems are there. In underdamped system, the pointer is oscillates sinusoidally like this and settles at steady final position. To settling the steady final position, the pointer takes more time. In overdamped system, there is no oscillations, but it takes more time to settle it final position. Slowly it settles at the final steady position. In critically damping system, the pointer is quickly moves to its steady position, final steady position, and there is no oscillations. Therefore, when the moving system moves rapidly but smoothly to its final steady position, the instrument is said to be critically damped or deadbeat. Generally, all measuring instruments are second order system type, and the damping ratio zeta is in between 0.6 to 0.8. This damping force is required only while moving system is in motion. For effective damping, damping is directly proportional to its velocity of the moving system. This damping torque is not affecting to the deflecting force or deflecting current of the measurement and not affecting the controlling torque of the instrument, and it is not affected to static friction of the instrument. Then it is said to be good damping system. The methods for producing damping torque are air friction damping, fluid friction damping, eddy current damping, and electromagnetic damping. This electromagnetic damping is used in galvanometers. Number 1, air friction damping. In this, the air friction chamber is shown here. The light-weighted aluminum piston is attached to the moving system. and the pointer is also attached to the moving system. If the pointer makes the oscillations, the piston on the air chamber is enter into the chamber or moves out of the chamber. The friction of the air inside of the chamber and the compression of the air and pressure of the air, this piston will oppose the oscillations of the pointer. This type of damping is very simple and cheapest way. Here the piston, the space between the piston and the air chamber walls is maintained uniformly throughout the chamber. Otherwise, this piston is twisted or bent and touched to the air chamber walls. The serious error occurs, which is solid friction error is occurred. Therefore, care must be taken in order to maintain a uniform space between the piston and air chamber walls. And this air chamber is fixed at one end and another one is piston mounted like this. When the piston moves into the chamber, the air inside is compressed and pressure of the air is also increased. That means the air inside is opposes the motion of the piston and hence the whole of the moving system oscillation is reduced. When the piston moves out of the chamber, the pressure in the closed space is reduced and pressure on the open side of the piston is greater than the outer side. Therefore, the again motion of the pointer is reduced. Like this, the oscillations of the pointer is damped out by air friction damping. Next, fluid friction damping. This is similar to the air friction damping, but in air chamber air is used, but here oil is used in the chamber like this. The viscosity of the oil is greater than the damping force of the damping system is greater. A moving disc is attached to the instrument spindle like this, and the disc is dips inside the oil and totally submerged in the oil. If the instrument spindle is oscillates, then the disc is also makes a movement inside the oil which submerged in the oil. The frictional drag between the disc and the instrument spindle always opposes the movement of the instrument spindle or the pointer. This way of damp out the oscillations in fluid friction damping. The frictional drag between the disc and the instrument spindle is used for damp out the oscillations. Next, another one, eddy current damping. It is a very effective damping which used in strong magnetic fields are available instruments. For example, permanent magnet moving type instruments. The principle of eddy current damping is whenever a conductor moves in a magnetic field, an EMF is induced in that conductor according to the Faraday's laws of electromagnetic induction. If that conductor is in a disk shape and a closed path is provided, the current is circulated inside the disk, which is known as eddy current. This current is interacted with the magnetic field to produce an electromagnetic torque which opposes the motion of the disk accordance with the Lenz's law. This torque is proportional to the strength of the magnetic field and the current produced in the disk. Here the current produced is proportional to the EMF of the disk, which produced by movement of the disk. That means the torque produced is directly proportional to the velocity of the disk. This type of velocity or movement of the disk or oscillations of the pointer is suppressed by making a constant magnetic field in eddy current damping. This type of technique is used in eddy current damping. The arrangements of eddy current damping is shown here. A circular aluminum disc is fixed to the spindle, which is movable in a magnetic field which produced by a permanent magnet or damping magnet, like this. When the spindle oscillates or moves, the aluminum disc also moves in the magnetic field. Then the EMF is induced in the aluminum disc. There is a eddy current is established in aluminum disc because there is several closed paths are available. According to the Lenz's law, this established eddy current disk is produces a electromagnetic torque in opposite direction to the oscillations of the disk or oscillations of the spindle. This damping force varies by varying the projection of the magnetic field on the circular disk. The eddy current damping is most efficient form of damping. It is very convenient to use in instrument where a metallic disc or a former and a permanent magnet already forms a part of operating system. Therefore, it is used in hot wire, moving coil and induction type instruments. This method cannot be used in moving iron and electro dynamometer type wattmeters because the introduction of the permanent magnet required for producing the eddy currents will distort the existing magnetic field, existing weak magnetic field. Therefore, it is not used in weak magnetic field instruments. There are two common forms of damping devices. A thin aluminum disc attached to the moving system. If this disc moves in the field of permanent magnet. a thin aluminium disc attached to the moving system. Number 1. Number 2. A metal forms which carries the working coil of the instrument. Number 1. The damping torque of a metal disc. The aluminium disc is attached to the spindle. Then the damping torque Td is equal to B square R square dBt omega by K into rho. Here B is the flux density of magnetic field, Webers per meter square. T is the thickness of the disc. B is width of the permanent magnet. D is the depth of the permanent magnet. Rho is the resistivity of the material of the disc. R is the radius measured from center of the pole to center of the disc. Omega is the angular speed of the disc, radians per second. K, a constant which depends upon the radial position of the poles. Damping torque Td equal to B square R square dB T omega by K into omega. This equation is used for discs or aluminium metal discs are used in eddy current damping circular discs. From the above equation, it is clear that the damping torque Td can be changed by changing the radial position of the poles with respect to center of the disc. Next, another one. In place of the aluminium disc, a metal former type is used. Then the eddy current damping is given by B square L square D square Bt omega by 2 rho into L plus D. Here B equal to flux density Webers per meter square, omega angular speed of the former, length of the former, width of the former. Here D equal to breadth of the former, where the resistivity of the former material in ohm meters. T is the thickness of the former. From the above equation, the damping torque can be varied by changing the thickness of the former. We have to learn earlier air friction damping, oil friction damping, and eddy current damping. In that, they compared with 3 damping systems here. In air friction damping is very simple and cheapest method of damping. But care must be taken that piston must not bend or twisted. That means it is not attached to the walls of the chamber. If it touches walls of the chamber, the serious error occurs due to solid friction. Therefore, this type of damping is used in moving iron electrodynamometer type instruments and also hot wire instruments. There is no need of strong magnetic fields in air friction damping. Therefore, it is used in weak magnetic field instruments like MI dynamometer type instruments. Next, in fluid friction damping, the oil which is required for damping can be used for insulation purposes in some forms of instruments which are submerged in oil. The oil which is used for Damping is also used for insulating purposes for some forms of the instruments. A vane moving in oil instead of air doesn't require the same small clearances to give effective damping. Therefore, this method is used in electrostatic type instruments, where the movement is suspended or rather than pivoted. Due to upthrust of the oil, the load on the bearings or suspension is reduced, thus reducing the frictional losses. These are used in only for instruments where vertical position only. These oil friction damping type instruments are used in vertical position only. Because of creeping of oil, the instrument cannot be kept clean. There is regularly maintenance of cleaning process for oil friction damping instruments. Eddy current damping is most efficient form of damping. It is very convenient to use in instrument area metallic disc or a former and a magnetic field already form part of the operating system. It is used in hardware, moving coil and induction type instruments. This is not used for MI type and dynamometer type instruments which has weak magnetic field. If we have to introducing the permanent magnet, the weak magnetic field is distorted, which distorts the deflection torque, which also affects the reading on the scale. The effectiveness of the damping order. The eddy current damping is more effective compared with the fluid friction damping. The fluid friction damping is more effective in compared to the air friction damping, because in air friction damping there is a uniform space is maintained between the piston and the walls of the air chamber, and it is very cheapest and simple method compared to the fluid friction damping. The fluid friction damping is used in vertical position only. The maintenance charges or maintenance is occurred for more for fluid friction damping. Next, eddy current damping. There is a small little bit. There is no need of air friction damping maintenance. Therefore, in this lecture, we have to complete the deflecting force, controlling force, damping forces. Thank you.